Hi everyone, my name is Reid and I'm one of Maptek's Global Development Strategy Managers, or DSM for short. I'm a software engineer by qualification from the University of Adelaide, and this is my first time presenting at a conference. Along with one of my teams, Evolution, and a colleague, Simon Ratcliffe, I've been working with Frank Neumann and Aneta Neumann from the University of Adelaide School of Computer Science on determining what effect uncertainty in geological models has on long-term mine scheduling. This work has been conducted as part of the Premier's Research Industry Fund, Unlocking Complex Resources. The project has two primary components, and today we're going to talk about the first stage of our work. If you ask a geologist or mine scheduling engineer how certain they are about their model or schedule, they might say that they're confident, or even that it's economically viable. But have you ever tried to quantify their certainty or the uncertainty in their geological model? Uncertainty is an inherent part of mining, and this project is the first step in quantifying this uncertainty, putting a value to the previously unknown. If you give two geologists the same drilling data and ask for a geological model, they'll come back with two models. They will share many similarities, but areas of uncertainty will likely result in different grades or even lithologies between the two models. Compare the areas highlighted in red on the two models here. These areas of uncertainty can result in massive differences in net present value when identified during long-term schedule creation. The ultimate goal here is to maximize the net present value during the lifetime of the mine planning. Quantifying the effect of uncertainty was stage one of the project, which is the main focus of today's presentation. It involved taking multiple models generated from the same drilling data and determining how the subtle differences between the models affected the resulting schedules, thus giving us a quantifiable measure of uncertainty. The second stage, which I'll cover at the end, aims to incorporate uncertainty as part of schedule creation to minimize the effect of uncertainty on the long-term schedule while maximizing NPV. Let's first cover some of the basic rules around mine scheduling that helped us formulate our problem, and then we'll dive into how we went about visualizing the effect of geological uncertainty on our long-term schedules. A block model is a 3D representation of a mineral deposit given by a set of blocks B. A set of destinations D are then assigned to each block during the optimization process. Each block has a number of parameters such as density, tonnage, ore grade, and many more. These parameters are used to determine the economic value of every block at a given time. For each block, we assume a revenue of R and a cost C if a block is sent at time T for processing. On the other hand, it encounters a mining cost M if it is sent to waste. In addition, the slope requirements for the set of blocks and other mining constraints are described by a set of precedence constraints P. In this formulation, the objective function, given by 1, seeks to maximize net present value of the solution based on a given discount rate. Constraints, given by 2, ensure that it is not possible to choose two different destinations for a block, and that an individual block is only chosen at one point in time. Crucial constraints are the precedence constraints, given by 3, which determine the extraction process of each block from the surface down to the bottom of the ore deposit. In order to provide for access and the stability of pit walls, it is not possible to mine a given block in a given time if the blocks in a defined pattern above have not already been extracted. The mining constraints, given by 4, ensure that the total weight of blocks mined during each period do not exceed the available extraction equipment capacity, known as the mining capacity. Similarly, the amount of material that can be processed in each period is restricted by the processing constraints, given by 5. So with that in mind, let's take a look at how Maptek proposes geologists generate the set of blocks. Domain MCF is one of Maptek's latest offerings. It uses machine learning to efficiently predict geological domains, requiring little in the way of input parameters. Because of the inherent nature of machine learning and predictive modelling, there are fluctuations in the resulting models when generated from the same input data. Generating multiple models from the same input data allows us to generate a measure of uncertainty on a block-by-block basis. For the purpose of this presentation, we'll call a collection of domain MCF geological models an ensemble. An aggregate geological model is generated by averaging the members of the ensemble. This aggregate model is used to create an ultimate pit, which is the maximum size of the pit we'll be mining. From here, we can split the model into stages. These stages allow us to divide the pit into more manageable sections and limit the search space for optimization purposes. This process is called stage design. Like many processes along the way, it too has an effect on uncertainty, but we'll talk about that a bit later. This staged ultimate pit provides the basis for long-term schedule creation using Maptek evolution strategy. Evolution strategy is a long-term strategic optimization software package which attempts to maximize NPV. Using some basic setup in the software, the information is sent off for optimization to AWS, where large populations of individuals can be evaluated, much faster than on our conventional desktop PCs. This process returns us an NPV optimized strategy mine schedule, showing yearly portions of the mine to be extracted. This is typically where conventional analysis stops and where uncertainty analysis can now start. Some keen observers out there might have noticed we haven't really done much differently to the steps an engineer would take to generate a schedule, apart from generating a few extra models at the start of the process. Well, here's where the changes start. Typical strategy optimization works on just one model, but we've implemented new functionality to allow it to work directly with ensemble run data from domain MCF. This generates us economics for each member of the ensemble, based on its own lithology and grades. This in turn allows us to compare each model, giving us some insight into the economic impact of geological uncertainty. In my sample data, I generated 10 members of the ensemble from the same composite data using domain MCF. After following the process I just mentioned for stage design and optimization, each member of the ensemble was processed through the strategy engine. For simplicity, they've been plotted here for us to see on a yearly profit basis. Preliminary results show that uncertainty in the geology can affect profit by up to $300 million per period. This is the difference between bankruptcy and new Ferraris for the company execs. A number of other supporting graphs showing profit and NPV variance were added to allow schedules to be analysed to judge how sensitive a project is to changes in geological interpretation, an aspect that has been overlooked in the past. This alone is a powerful decision-making tool for making adjustments to drilling programs and pit designs, but these charts can't make the decisions for you. They can be used to educate all interested parties on where uncertainties lie and how they can affect the overall goal of getting ore out of the ground. So how can we use this information to affect our decisions? Strategy is designed in such a way that changes to the setup are relatively simple, allowing any change to be quickly visualized in a new schedule. Changes in the drilling program can assist by focusing on areas of higher uncertainty, allowing new composite data to be processed by the system. Changes to the pit design may move areas of high uncertainty to be mined together with areas of high certainty. Overall, this would likely result in a lower NPV, but will greatly improve certainty around the deposit. So where to now? Well, our path forward focuses on two separate areas of the scheduling workflow. First, we'll adjust the boundaries of individual stages within a model to shift when and how much material is mined. This in turn should affect the proportion of uncertainty accepted in each stage. Second, we'll adjust the schedule optimization process to downweight solutions that have a high degree of uncertainty, making more certain solutions look better and more likely to be part of the resulting schedule. Since we have to accept the uncertainty at some stage, the current goal is to push as much uncertainty to the latter portions of the schedule where the time value of money is lower. That concludes today's presentation. A big thanks to Steve Sullivan and Simon Ratcliffe from Maptek, and Dr. Frank Neumann and Dr. Aneta Neumann from the University of Adelaide School of Computer Science for their involvement in the project so far. Thanks for watching.